Given the truss structure with the following parameters, h is 0.7 meters, b2 is 0.1 meters, b1 is 1 meter, and we see that this point is completely fixed. Here we have a horizontal displacement, and here we have a vertical displacement. The material parameters are given as well, and the coefficients alpha 1 and alpha 2 needed for determination of a damping matrix are given as well. We have to pre-compute all required initial data and solve using central difference scheme. Mass matrix given as following. The stiffness matrix of the structure is given as well. Time periods of structural degrees of freedom T1 and T2 are given here, and in the further exercises and lectures we will learn how to determine them. Load for determination of initial displacement in static calculation is given here, and the initial velocities are assumed to be 0. Such a task can occur in exam. That's why we will solve it using hand calculation. We will solve for the first 2 time steps. I will not be uploading this Jupyter notebook in Moodle. That's why I'll leave for you implementation of the code or in any language, in MATLAB, in Python, or in C++, and plotting the results for this structure.
We start with the pre-process, estimating the damping matrix based on the Rayleigh assumption in the following way. So damping matrix C is equal to alpha 1 times m plus alpha 2 times k, where alpha 1 and alpha 2 are our coefficients which are given. M is the mass matrix, k is the stiffness matrix. So inserting the values, we obtain the following matrix with the units kilograms per second. We also need to determine the time step to obtain the stable solution. So delta time critical, it is obtained as the minimum of the time periods, the mean over pi, and we had T1 and T2 time periods were given, and the minimum will be T2 for the second degree of freedom, so for the vertical displacement it will be over pi. So obtain the value 5 seconds. Size of the time step shall be smaller than this value, so we take it equal to 1 times 10 to the power minus 4. Now we also need to calculate u displacement u at time step minus 1. We need it because we have to start our algorithm at the 0th step using displacement at minus 1. So first we calculate the initial displacement for the given load for the static in a static calculation. U0 will be inverse of stiffness matrix times load F. So inserting K, inserting F, we obtain in meters. Now we calculate initial acceleration from this equation, so m u dot 0 plus damping matrix C u dot 0 plus stiffness matrix K u 0. And the acceleration can be then written as u dot 0 minus C u dot 0 and we multiply it times the inverse of mass matrix M. u dot 0 is equal to 0, so this term is equal to 0, and our acceleration will be inverse of mass matrix minus, here is k u. Inserting mk and u0, which we have obtained here, we obtain now the values of initial acceleration, 0, and the units are meter per second square. The displacement at time step -1 can be determined as follows. Acceleration we just found in the previous slide, and the velocity, this part will be 0. The displacement at time step -1 will be equal to this vector. Units is meters. In the last step of preprocess, we determine the effective stiffness matrix in the following way. Mass matrix M, time step delta T, damping matrix C over 2. Here we obtain the following matrix. With units newtons per meter. Now we start with the calculation of solution, where the displacement at step n+1 can be found from this equation, and the expression for F effective is given as the following. So F external is the external load. The subscript defines here the time step. So we have here displacement at time step n, displacement at time step n, and these two guys, displacement at time step n-1, which we found which will, in case our n is 0, then we'll use this displacement. Let's write this equation for the 0th time step. So this is how it would look like. These displacements have been obtained at the preprocess, and since we're applying an initial displacement, our external load will be equal to 0. And inserting all the displacements matrices into this equation, we obtain F effective at the 0th time step as the following vector. And the units of the vector are newtons. Given the K effective and F effective, the displacement U1 can be found by multiplying the inverse of K effective times F effective. Here we obtain the following vector. In meters. We can calculate the 0th initial velocity, so initial velocity at u dot 0, to check whether our calculation has been correct or not. So if we now insert here u1, which we obtained, and u minus 1, we'll obtain that u dot 0 is equal to 0, what is consistent with the problem definition. So we verify that this step we've done correctly. So now we can continue a calculation at a time step n is equal to 1. Again, we have to calculate the F effective. Our external load is 0, and here we have to insert u1 at the time step 1 and u0, and of course the matrices C, M, K, and after inserting them we obtain the following results. In newtons. And now again we can find the displacement 2 by multiplying the inverse of K effective. K effective is we calculate it only once in the beginning of the calculation solution in the preprocess, and we don't have to update it at each time step. And then we have to multiply inverse of K effective times F effective, and we obtain the following results. In post-process, we can calculate the velocity u dot 1 as follows: 1 over 2 delta t u. So this is how we do it at the time step n plus 1, but n is equal to 1, but we can do it at each time step. Units are meters per second, and we can also obtain the acceleration u dot 1. We use the following expression. And obtain the following result for the acceleration u dot 1.
Once more, your homework is to implement the central difference scheme for the given structure in any language which you like to. I've done it here in Python, so I can compare my handwritten results with the results which I obtained with this code. So solution at time step n0, displacements are here, and the time step n is equal to 1. Then the displacements, if I compare them to my handwritten results, I see that they are the same, so my handwritten calculation is verified. I can also plot these results. For example, here the displacements of both degrees of freedom, we see that oscillations are damped with time, the effect of damping. And I wanted to show you the effect of the size of the time step. So our critical time step size is 0.005. So if we take now something bigger than that value, we see that the solution blows up to infinity.